Hello, everybody. So we welcome our new participant of this seminar, Gabriel Nivasch from the University of Ariel from Israel, with the new and surprising result, new combinatorial independent principle from Peano Arithmetic. So he will speak about fusible numbers and Peano Arithmetic.
Okay,
welcome.
You very much. Okay, so I'm going to talk about fusible numbers and Peano Arithmetic, and this is joint work with Jeff Erickson and Junyang Tsu. So this talk, I'm not going to get into the technical details, and probably going to say many things which are quite basic, but I made a talk for all the audiences. So I'm using this. I'm going to use this presentation for all my talks. But anyway, I hope it's interesting. So I first want to show you this strange recursive algorithm, M of x. So this algorithm M given an input x, which is a real number. If x is less than 0, it returns minus x. Otherwise, it returns M of x minus M of x minus 1 divided by 2. So let's see what happens. For example, what's M of 1? So here, you first have to calculate M of 0. And we won't go into the details, but M of 0 turns out to be a half. And then you do 1 minus a half is a half. So M of a half is a quarter. So divide a quarter by 2, you get an 8. So M of 1, it returns 1/8. And M of 1.5, so you first have to compute M of 1/2, which we said is a quarter. And then you do 1.5 minus a quarter is 5 quarters. And that turns out to be 1/16. So 1/16 divided by 2 is 1/32. And let's see what happens if you compute M of 2. Then it gets a longer, and at the end you get 1 divided by 1024. So M of 2 is 2 to the minus 10. And then you can compute M of 2.5, and it gets really long. It's a few pages. And at the end you get 1 divided by this huge number, 2 billion and something. So M of 2.5 is 2 to the minus 31. And if you don't want to try M of 3 on your computer, because it will take forever, but we know analytically that M of 3 equals 2 to the minus 1.5 billion and something. And the question is, does this algorithm actually terminate for every x? By the way, feel free to ask questions or comments. So this is this algorithm. So let's see. This recursive call on which you subtract 1 is okay because you'll get down to 0 in a finite number of steps. But this one is not so clear. It's okay because this guy can return an arbitrarily small number. So you do x minus a tiny bit. But nevertheless, this algorithm terminates for every real x. Though that's not so easy to prove. And in fact, Peano Arithmetic cannot prove that algorithm M terminates for every natural x. This is one of our main results. So let's talk about fusible numbers. So there's this old puzzle involving fuses, and it goes like this. You have a few fuses. Each one burns for exactly 1 hour, and you want to measure 45 minutes. And you cannot cut the fuses in half or anything like that. Let's say the fuses don't burn uniformly, so that's not allowed. So how do you measure 45 minutes? So the solution to this puzzle is like this. You take 2 fuses and you light both ends of one fuse simultaneously, and also at the same time, one end of the second fuse. So then the first fuse burns after 30 minutes. And then at that point, you light the second end of the second fuse, and it burns for an additional 15 minutes. So that's how you get to 45 minutes. So based on that, we can ask what other times can we measure this way? So we call a real number x fusible if you can measure x hours using a finite number of 1-hour fuses. And the rules of the game are that you can light the fuse ends either at the beginning or at an instant in which another fuse completely burns. And you can light many fuses simultaneously, that's okay. So formally, the set of fusible numbers is defined recursively this way. 0 is fusible, and whenever you have two fusible numbers whose difference in absolute value is less than 1, also a plus b plus 1 divided by 2 is fusible. Because if you have a fuse and you light one endpoint at time A and the second endpoint at time B, then it burns at time a plus b plus 1 divided by 2, which we denote by A fuse B. So these fusible numbers were first introduced by Jeff Erickson in around 10 years ago at some Gathering for Gardner event in Illinois, and he presented some results in that talk. And note that in this definition, we don't allow lighting a fuse only one endpoint and then let it burn completely in time 1. But that entails no loss of generality because you can measure 1 unit of time using two fuses in this way. Mm-hmm. Okay, so this is how the set of fusible numbers looks like. So here you have a half, which is 0 fuse 0, and 3/4, which was what we had in the riddle. And then you have 7/8, 15/16. You get all these fusible numbers that converge to 1. And also 1 itself is fusible because you can get it by 1/2 fuse 1/2. And then you can apply a half to all these fusible numbers, and you get all these fusible numbers, and you can apply a half again. So you get, so if here you have a limit point, here's a second limit point, and then a third limit point, and here you have a kind of double limit point, and then you can apply 3/4 to all these guys, and you get another double limit point and another double limit points, and here you have a triple limit point, and you can apply 7/8 to these guys, and here somewhere over here you have a quadruple limit point. And so every fusible number is a dyadic rational, meaning a fraction whose denominator is a power of 2. And there might be several ways of obtaining a given fusible number. For example, 5/4, there are these two different ways of obtaining it. So now we're going to prove that the fusible numbers are well ordered in the real numbers, which means that they contain no infinite decreasing sequence. So the proof goes as follows. Suppose, okay, so here's some pedantic footnote regarding the axiom of choice. I'm not using the axiom of choice, it's okay. So suppose for a contradiction that you do have infinite decreasing sequences in the fusible numbers. Mm-hmm. Each such sequence has a limit, and there must be a smallest such limit, because a limit of limits is also a limit of fusible numbers. So let L be the smallest limit of the decreasing sequence of fusible numbers. Okay, so here you have this limit L. And all these fusible numbers are obtained by fusing two fusible numbers. So Z1, Z1, Z2, Z3 are obtained by X3 fuse Y3, where we assume X is the smaller of the two. And so without loss of generality, you can assume that the sequence X is either increasing or decreasing or constant by taking a subsequence if necessary. So if, for example, you can get that by applying the infinite Ramsay theorem. And but x cannot be decreasing because the difference between x and z is always at least a half. So if that would be the case, then x will converge to a limit smaller than L. And we said L is the smallest. So L has to be constant or increasing, and therefore y has to be decreasing. Okay, and if x is constant, you get something like this. Here's the first, so x, all the xi's are the same, they're here. And here's the first z and the first y. And here's the limit of the z's. And so the limit of the y's has to be smaller than L. And therefore, that's a contradiction to the minimality of L. And if x is not constant but increasing, then it's even worse because as this guy moves to the right, these guys move to the left in order to keep this guy in place. Okay, so that's basically the proof. Okay, the next result is that F is closed, meaning it contains all its limit points. So suppose for contradiction that F is missing some limit points, then there must be a smallest missing limit because otherwise there will be an infinite descending sequence of missing limits, and that will give you an infinite descending sequence in F, which we just proved is not the case. So let L be the smallest missing limit. Again, you have so these guys are fusible numbers, but the limit is not a fusible number. And each of these guys is composed of an x and a y, where x is the smaller of the two. And without loss of generality, both x and y are non-decreasing by taking a subsequent if necessary, because we already proved they are not decreasing infinite sequences. So each of these sequences has a limit, which we call little x and little y. And by continuity L, this guy is x fuse y. So if we prove that x and y belong to F, that means that L also belongs to F, and that's a contradiction. Okay, but x for sure belongs to F because x, as we said, is smaller than L minus a half. And we said that L is the smallest missing limit. So x cannot be missing. The question is what happens with y. So if y is between x and L, then y is not missing either, and L is not missing either, and we get a contradiction. And the other possibility is that the distance between x and L is exactly 1, and y actually equals L. Okay, but recall that x is just a limit of the x's, and y is the limit of the y's. But in this case, since x we know is not missing, you can get L this way. And again, L is fusible. So we get a contradiction also in this case. Okay, so we conclude that the fusible numbers are closed. Okay, now some little background on ordinals. As I said, I suspect all of you know this stuff. It's going to be quick in any case. So a totally ordered set is well ordered if any non-empty subset has a smallest element, which, if you don't mind using the axiom of choice, all means that it contains no infinite descending sequence. And if you have two well-ordered sets, one is isomorphic to initial segment of the other. So here you have two well-ordered sets, and you start pairing them up from the bottom up, and you'll get that B is an initial segment of A, so or A is an extension of B. So if you group together well-orders into equivalence classes, those equivalence classes are themselves well-ordered by extension. Why are well-orders important? Because this thing called Transfinite Induction, which says that if you have well-ordered set, and there's some property that whenever it holds for all smaller elements and some element, it also holds for that element, then that property holds for the whole set. And there's this, so you like to have a canonical representative of each equivalence class of well-orderings, and von Neumann invented a very nice way of doing that, which is by using containment as the relation. And So these are what is called the ordinals. So each ordinal equals the set of all the preceding ordinals. There are operations on ordinals, you can add them up. So alpha plus beta is putting beta after alpha, which is not the same in general as beta plus alpha. Alpha times beta means replacing each element of beta by a copy of alpha, which in general is not the same as beta times alpha. There's also alpha to the beta, which we won't get into. There's limit of a set of ordinals, which is basically the union. If you write them in the von Neumann definition, there are the ordinals come in two types: successor ordinals and limit ordinals, whether they have an large limit or not. And there's epsilon zero, which is this limit ordinal. And there's each ordinal less than epsilon zero can be uniquely written as this sum of exponents of omegas, like this, for example. Okay, and now we're going to prove that the order type of the Fusible numbers is epsilon zero. Okay, so this theorem contains both a lower and an upper bound. So let's first do the lower bound. And so we're going to construct a subset of fusible numbers, f prime, whose order type is exactly epsilon zero, and that will prove the lower bound. And this f prime, these fusible numbers, we'll call them tame fusible numbers. And you construct them this way. You first start with these fusible numbers that converge to 1. And so far we have defined f prime up to 1, and 1 is a limit point. So you do the following. You go distance 1 left, in this case to 0. Then you go right to the next fusible number, and you cover some distance m. And then from 1, you go left this distance m. And then you use y, you apply y on all these guys infinite many times, and you define the fusible numbers up to here. And this is again a limit point. So you do ordinal induction on this process. In general, suppose you have defined the tame fusible numbers up to some number x plus 1, and suppose that it's a limit point. So you go distance 1 left back to x. You go right to the next fusible number, covering some distance m. And from x plus 1, you go left distance m. And you apply y on this interval infinite many times, again and again and again. And you define the tame fusible numbers up to y plus 1. And so now to define the up to y plus 1, it's again a limit point. So you have to do this infinite many times by ordinal induction. And so these are the tame fusible numbers. And now let's see what their order type is. So we first claim that if the order type of x is alpha in the tame fusible numbers, then the order type of x plus 1 is omega to the alpha. The proof is by ordinal induction. So suppose that the order type of x is alpha, and the order type of x plus 1 is omega to the alpha, and let y be the guy that comes after x. So the order type of y is alpha plus 1. And we want to prove that the order type of y plus 1 is omega to the alpha plus 1. Okay, this is the induction step that we want to do. So since what we do is we take this final segment and copy it infinite many times, and this final segment also has order type omega to the alpha. And you copy it again and again and again, so you get omega to the alpha times omega, which is exactly omega to the alpha plus 1. So that's basically the proof. For limit ordinals, you do a limit argument, and that's it. So basically, what this means is that the ordinal type, if the ordinal type of 1 in the tame fusible numbers is omega, then the order type of 2 is omega to the omega, and so on. You get a tower of omegas each time the tower gets taller and taller. So the order type of the whole set is epsilon 0. Okay, so that proves the lower bound. We know that not all Fusible numbers are tame. This is the smallest counterexample we know. 4889 divided by 496. So if it were tame, the way to obtain it will be that you go the distance one left to here, and then you use it by using this black guy. But you cannot get 4889 divided by 496 using this black guy, but rather by using 19/16 and fusing it with this other guy. So this guy is not tame. Okay, so now let's compute. Suppose I give you a real number R, and I want to know what's the distance from R to the next tame Fusible number, meaning we take the smallest Fusible number that is larger than R, and that minus R. Okay, well, let's call that M of R. So how do you do that? So R is formed by going distance ones left to R minus 1, and then using the next Fusible number, which is Y in the picture. And the distance between this and this is by recursion M of R minus 1. And then if we go this distance left from R, we get this Fusible number Z, which equals R minus M of R minus 1. And if we do Y fuse Z, we get exactly R. But we don't want to get exactly R, we want to get something larger than R. So what we want to do is get smallest tame Fusible number after Z. Just 1 second. Okay, we want to get the next tame Fusible number after Z, and the distance to it is M of Z by recursion. Let's call it W. So we want to do Y fuse W. Okay, that's what we want. And the distance from R to that guy is half of this distance. So get M of Z divided by 2. So you get this recursion. M of R equals M of R minus M of R minus 1 divided by 2, which should sound familiar to you. So now you know what the mysterious recursive algorithm does. It computes the distance to the next tame Fusible number, which is at least the distance to the next Fusible number, not necessarily tame. So now let's talk about the rate of growth of the density of Fusible numbers, because Fusible numbers get more and more dense as you go up, as you saw in the pictures. And the question is, how fast do they get more and more dense? And okay, so as R grows, let's talk about, let's say, just the tame Fusible numbers. As R grows, M of R goes to 0, so 1 over M of R goes to infinity. So how fast does this function go to infinity? And the answer is very fast. Okay, so let's talk about fast-growing functions. So first, this thing called Ackermann's function, which is a very fast-growing function. In order to define it, you first define the Ackermann hierarchy. You start with the function A1, which given n returns 2n. And then A2 is defined by applying n times the function A1, starting, let's say, with 1. So A2 of n is basically 2 to the n, because you multiply by 2 over and over and over n times. And then A3 is applying A2 n times. So A3 is what is sometimes called the tower function. It's a very fast-growing function, but you can keep going more and more. Apply A4 of n is applying n times A3 of n, and so on. And in general, you get this recurrence relation. And AK grows faster than any number of compositions of AK minus 1. So it's like this. AK minus 1 is a very fast-growing function. And if you compose it with itself C times, it's even faster growing. But AK grows even faster than that. And then you define Ackermann's function by sort of columnizing this two-dimensional table. So A of n is defined as A n of 3. and this function grows faster than any AK. Okay, so that is a very fast growing function, but you can ask, well, can we do things that grow even faster? And the answer is yes. Well, you can, for example, define B of n to be n times composing the Ackermann function. And then we could say that C of n is composing B of n n times, and then D of n, and so on. And then we could take, let's say, psi of n to be the columnizing take on the functions A, B, C, D. Okay, but then you start kind of getting confusing how to represent all these functions. The solution is to use ordinals. So for that, we need to talk about canonical sequences. So if you have an ordinal below epsilon 0, there's a way of defining a sequence that converges to alpha. It's like this. It's basically replacing the rightmost omega by n. Okay, so alpha square brackets n is replacing this rightmost omega by n. So for example, if you have this ordinal, you first write it this way. Okay, so replace the rightmost omega by n. So you get this ordinal. So as n goes to infinity, this guy converges to this guy. Okay, the limit of alpha n is alpha. Okay, and then you have this fast growing hierarchy, which is also called the Wiener hierarchy, up to epsilon 0. So we have a collection of fast growing functions indexed by ordinals. So one way of defining it will be like this. You start with function 2n. For successor ordinals, you do composition n times. And for limit ordinals, you sort of columnize on the sequence that converges to alpha. Okay, and then you get these functions that we mentioned before. You get the Ackermann hierarchy and the Ackermann function, and we get these functions that we call B, C, and so on, and the function we call psi is actually f omega 2 of n. But the actual definition that people normally use is slightly different, just for technical reasons. Instead of putting here 1, you put here an n, and instead of putting here 3, you put here an n, but it's basically the same thing. Okay, and for every two ordinals, alpha and beta, f alpha overtakes any number of compositions of f beta. And then to top this up, you take a canonical sequence that converges to epsilon 0, which is this tower of omegas, and you define f epsilon 0 of n to be this. And so f epsilon 0 is a tremendously fast growing function because it overtakes f alpha for any smaller ordinal alpha. Okay, and what we prove is that this 1 over mn, which we talked about before, the inverse density, or the density, it actually grows to infinity like f epsilon 0. Okay, and I'm not going to get into the details of the proof too much. So the tame fusible numbers get very dense very quickly. I'm just going to give you a sketch of how the proof goes. So you first notice that the tame fusible numbers behave like this. If you have a fusible number gamma, where gamma is some ordinal, and the next guy is this fusible number, okay, gamma plus 1. So these are ordinals. These are not real numbers, and so this number you want to compute, this m, the distance between this and this is 2 to the minus something. This minus something, call it d of gamma. So if you go left instead of going right the same distance, you bump into one of the guys in the canonical sequence of gamma. Let's say gamma 5. Okay, it's not necessarily 5. And if you go a half of that, you find gamma 6. And if you go a quarter of that, you find gamma 7. Okay, it's not always 5, it's always some number, and then you get the next number and so on. Okay, and that number which here in this example is 5, we call it xi of gamma. So you have d of gamma and xi of gamma. And we have these recurrence relations for d and xi. They look very scary. They are very scary, but it's not too hard to check them. It's just tedious. And it's just going over the construction and checking all these cases. And what we want to show is that this d grows very fast, okay? Because this is the exponent, the 2 to the minus something. And so if we had here, let's say the Wiener hierarchy recurrences, we'll say, well, it's obvious. But we don't have, we have some very complicated and quirky thing here, and we have to work hard in order to make sense of this and to get some lower bound. And a useful tool is to use something called the Hardy hierarchy, which is sort of the younger sibling of the Wiener hierarchy. It's defined a little differently. For a Hardy of alpha plus 1, instead of composing n times, you just add 1 to the input of Hardy of A. But for the limits, you do the same thing. And it turns out that F alpha is the same as Hardy omega to the alpha. So even though this grows slower, it doesn't grow that much slower. And so what we do is, working very hard, we show that d of omega to the omega to the omega to the omega to the alpha times n is at least Hardy alpha of n. And that's how you get this fast growth, this lower bound. Okay, so I'm not going to give any more details.
So am I right that in order to get this lower bound for density, so you also only consider these tame numbers, right?
Yes,
Or,
this is a recurrence
So
for
this-
the tame fusible numbers, which are a subset of all the fusible numbers. They are easier to work with, so we can do it. Yeah.
So essentially, you compute this density of tame numbers, and it's roughly the same as full density, so to say. That's
Well, actually, we
way.
don't have an upper bound. We don't know an upper bound about the density of all the fusible numbers. That's one of the open problems, but we expect it to be so. I'm gonna have it in a slide
Okay.
Okay. Okay. So now let's talk about upper bound. So now we're going to prove that.
I have a question about what you said before. So do you have some conjecture about how close your 4 exponentiation tower to the optimal estimation of the growth rate of?
It should be the same. It should be the same, though. I think the easiest thing to prove is the easiest upper bound to prove is a tower.
Okay, so but you think that already just d function should grow something?
No, actually, we conjecture that it's pretty much the same. I'm going to show a conjecture at the end.
Oh, okay.
And I'll see. It's supposed to be. That's supposed to be right. I'll show you at the end. But now let's talk about the upper bound of all the fusible numbers. And we show that the upper bound of all the fusible numbers is at most epsilon 0. So here we need to talk about some more background. So there's this operation, which is called the natural sum of ordinals. So we have the sum of ordinals, and there's also the natural sum. The natural sum is what you would expect the sum to be. A commutative and associative. Basically, you take all the terms and you order them in decreasing order. Okay, like in this example. And it's different from the usual sum. And there's also the natural product, which is basically distributing using natural sum and also distributing in the exponents. And there's this thing about well-partial orders. So suppose you have 2 disjoint well-ordered sets A and B, and you take their union, and you define a partial order on the union. And the partial order is like this. If both x and y come from A, or they both come from B, then you compare them according to A or according to B. Otherwise, they are not comparable. Okay, so you have this partial order on A union B, and you ask, well, I would like to extend this partial order into a total order, which means basically sticking in A into B in some way without changing the relative order in A. And the question is, what is the largest possible order type you can achieve this way? This extension of a partial order into a total order is called a linearization. So what's the largest order type of a linearization of A union B? And the answer is the natural sum. Okay, if the order type of A is alpha and the order type of B is beta, then the maximum order type of a linearization is alpha natural sum beta. Okay, this is a result by Dion and Parry from 1977. And you can also define, given two well-ordered sets A and B, the Cartesian product and define a partial order on them. Like this, so you have an element of the Cartesian product, has a little a and a little b. So if both the little a's are compared and in one direction and the b's in the same direction, then the pair is also compared in that direction. Otherwise, they are not comparable. Okay, so I have this partial order on the Cartesian product. And if you ask what is the maximum order type of a linearization of the Cartesian product, the answer is the natural product. Okay, this in the same paper. So what we have to notice here is that if we have two well-ordered sets, let's say two sets of fusible numbers, and we fuse each element of A to each element of B, this is basically doing a Cartesian product, and the order here is some kind of linearization of this partial order. Why? Because if you increase both little a and little b, the result will increase, which is exactly what's said here. Okay? Using this, we can prove that if the order type of x in fusible numbers is alpha, then the order type of x plus 1 is at most omega to the alpha. Let's see why. So this again by ordinal induction. Okay, so suppose here's the proof. Suppose by induction that the order type of x is alpha and that the order type of x plus 1 is at most omega to the alpha, and let y be the next fusible number after x. So its order type is alpha plus 1. And we want to prove that the order type of y plus 1 is at most omega to the alpha plus 1. Okay? So let's look at a certain interval. So we have these intervals, I0, I1, I2, which are defined as before. So I0 is obtained by going backwards the same distance that you go from x to y. Okay? So let's say you have a certain fusible number z in some interval in, let's say in I2. And z is obtained by fusing u and v. So can it happen that v belongs also to the same interval? And the answer is no, because with whom do you fuse v? You have to fuse with some u. But if you take u to be x, then it's too small, because the distance between u and v is larger than 1. So that's not allowed. And if you take u to be y, which is the next guy, then that's already too large, because already when you fuse y with the left endpoint of I2, you go to the right endpoint of I2. You completely skip I2. Okay? So it's impossible for v to belong to the same interval as z. Okay, so that means that v has to belong to this J1, okay, from the beginning up to here. Okay? And therefore, the fusible numbers in the nth interval are obtained or are a subset of fusing all the guys in Jn-1 with themselves. Okay, this is some kind of an upper bound for them. So it means that the order type of I1 is at most omega to the alpha multiplied by itself. And that's also, okay, that's the upper bound for the order type of this part, which of course is also an upper bound for the order type of the whole thing, because the order type of the whole thing is this plus this, but this completely dominates this, okay? And then the order type of I2 is at most this multiplied by itself, and the order type of J2 is at most this plus this plus this, this dominates, and so on. Okay, and you get omega to the alpha times omega in the first exponent, so you get omega to alpha plus 1. Okay, and then for limit ordinals, you use a limit argument. So you get this upper bound for the ordinal type of the fusible numbers 1, 2, 3, and 4. So you get this upper bound, this tower of omegas, which grows by 2 in each step. And if our conjecture is true, then it grows by 1 in each step, not by 2. But in any case, for an upper bound of epsilon 0, this is good enough. Okay, so but we would like to have an upper, what?
No, it's okay. It's
Okay.
very nice.
So we know the order type, an upper bound for the order type, but that doesn't give an upper bound for the density. And so this is an open problem. If anyone wants to work on it, they're welcome. Okay, so now we're talking about Peano Arithmetic, now the fun part. So I'm again going to say all kinds of things that you already know, probably. So there's this thing called first order arithmetic, which is a language that uses these symbols exist for all and or not, plus, times, successor, and 0, and equality. And the domain is and you have variables which can represent natural numbers, and the domains are the natural numbers. And you can represent all the natural numbers using the successor and the 0. And you can have all kinds of sentences. For example, this is a true sentence. For every x, there exists a y such that x plus 2 equals y. This is a false sentence. For each x, there exists a y such that y plus 2 equals x. This is false because we're on the natural numbers. And you can express all kinds of notions. For example, x less than y, you can say there exists a z such that x plus z plus 1 equals y. So here you have a formula in which x and y are free variables, and z is a bound variable because it's bound to this quantifier. And you can represent x mod y using some formula which has, so x mod y equals z, by some kind of formula that has a z as x, y, and z as free variables. And you can, for example, say that a certain number x is prime, and you can write the beautiful theorems, like, for example, the Green-Tau theorem that says that the prime numbers contain arbitrary long arithmetic progressions. So this beautiful theorem is written very succinctly in first order arithmetic. There's, for example, Goldbach's conjecture that every even integer larger than 2 can be expressed as the sum of 2 primes. And you can write things about natural numbers and primes, but can you write other things? And for that, there's this thing called the pairing function, which allows you to represent a pair of numbers as a single number. It's given by this function, and this function is a bijection between n squared and n. It goes like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in diagonals. And you can write the relation, the pair AB equals C, as this first order formula. And you can represent any k-tuple of numbers as a single number if you nest this pairing function. But in order to access these numbers A, B, C, and D using first order arithmetic, k has to be fixed in advance before you write a formula. So it's a little problematic. And Gödel asked, how can you represent a finite sequence and access its elements in first order arithmetic if you don't know the sequence length in advance. So some people claim that Gödel found with God in order to find the solution. In any case, the solution that Gödel found is like this. Suppose you want to represent this sequence A0 up to AK minus 1. So all you have to do is find a number n and an arithmetic progression of moduli such that in mod these guys gives you as remainder the sequence that you want. And specifically, you can take this sequence to be I plus 1 times n plus 1. All you have to do is find n, okay? And the Chinese remainder theorem guarantees that it's always possible because you can make sure that these guys are both large enough and relatively prime to each other. And then you can represent your whole sequence as a triple k and m. The length of the sequence, n is the number you put here, and m defines the arithmetic progression of moduli. And here's an example. Suppose we want to represent this sequence of length 4. Then you can do it this way. And you could represent as this single number, this huge single number encodes this sequence of length 4. And this is a first order formula that says that the ith element of the sequence is encoded by number x is a. Okay, so you can do in first order arithmetic arbitrary length finite sequences. And with that, you can do many things. You can do exponentiation, for example, using this formula. You can do factorials, Fibonacci numbers. You can do discrete structures like trees, graphs. You can do rational numbers. You can do algebraic numbers. You can even do Turing machines. You can do many things. There are things you cannot do in first order arithmetic. You cannot quantify over all reals. You cannot quantify over all infinite sequences, over all infinite sets, because those are second order statements, which you can do in second order arithmetic. But in first order arithmetic, you can talk about specific reals such as pi and e, or you can quantify over infinite sequences in which each element is determined in some predefined way by the previous elements. Okay, so for example, in first order arithmetic, you can write a formula that says that z, the rational number z is fusible. You write like this: there exists a finite set of rationals S that contains z, and such that for every x in this set, either it's 0 or there exists two other guys in the set whose difference in absolute values at most 1, and such that x is y fuse z. Okay, and you can also talk in a first order arithmetic about this algorithm, this recursive algorithm M. You can write a formula that says that M terminates on the rational number R, outputting Y. Okay, you can do something similar. Okay, there's this thing called Peano Arithmetic, which is a set of axioms and rules of inference for first order arithmetic. And among the axioms are the induction axioms. So you have infinitely many induction axioms, one for each possible formula. So for each formula phi, you have an axiom that says that if phi of 0 is true, and for every n, phi of n implies phi of n plus 1, then phi of n is true for every n. And the PA theorems are all the sentences that can be derived from the rules by the axiom, by the rules from the axioms. Okay, and so all PA theorems are true because the axioms are true and the rules follow logic. But is every true statement a PA theorem? And as you already know, Gödel proved that the answer is no, not only in Peano arithmetic, but in any formal system strong enough to support basic arithmetic. And Gödel actually constructed a specific complicated sentence with G, which is true, but is not a theorem of the system. But this sentence G is very artificial, and people started wondering if there are any natural truth statements that cannot be proved in Peano arithmetic. And then we got the first result in that direction was by Gentzen, who proved that PA cannot do ordinal induction up to epsilon 0. So he found a specific formula phi for which PA cannot prove this sentence, which is basically a ordinal induction up to epsilon 0 specific to the formula phi. There's at least one formula for which PA cannot do ordinal induction up to epsilon 0. And then later Paris and Harrington came and they found this beautiful theorem regarding some Ramsay like statement. So you have if you have a finite set A and you take all the k tuples, you can in a finite set of colors, you can color all the k tuples, and then a subset B of A is called monochromatic if all the k tuples formed by that subset B are all of the same color. And then if your set is a set of natural numbers, you say that the set is large if it has more elements than its minimum element. And then Paris-Harrington proved that for every k, c, and n0, there exists n1, such that no matter how you color the k tuples of the numbers between from n0 to n1 with k colors, the k tuples, then you always have a large monochromatic subset where large is this, okay? So, and they proved that this theorem, even though it's true, it cannot be proved in Peano Arithmetic, okay? The easiest way to prove this is by using the infinite Ramsay theorem. The problem is that this is a second order statement. That gives you an idea of why PA cannot prove it, because the obvious proof doesn't work. Later came the Goodstein sequences, which is like this. You can write a number in any notation base that you like in base 5, and you can write it in a hereditary base 5 notation. And then given any number, you do like this. You first write it in hereditary base 2 notation. Then you replace each 2 by a 3 and subtract 1. Then you write it in hereditary base 3 notation. Then you replace each 3 by a 4 and subtract 1, and so on. And no matter which n0 you take, you always go down to 0. Even though at the beginning you start going up and up and up, and then you start going back down, okay? And Peano Arithmetic cannot prove this, okay? And the obvious proof of this is using the fact that ordinals below epsilon 0 were ordered, but this is something that PA cannot do. Okay, there came the hydras. Okay, so this is a hydra. It has internal nodes and heads. The heads are in blue, and Hercules comes at each step and cuts off a head, whichever head he wants. And then the hydra does like this. Let's say Hercules cuts this head. Then you take this edge E, which is below this edge, and the hydra picks some number k and sprouts k copies of everything that's above E, including E. Okay, so if k equals 2, then the hydra sprouts 2 new copies of all this part, and now you have 3 copies. And then Hercules comes again and cuts some head. In this case, the hydra doesn't do anything because this head is attached to the root. Okay, and Hercules keeps doing this. Okay, so you can prove that for every initial hydra, no matter which head Hercules chooses at each step, and no matter which sprouting numbers, K1, K2, K3, the hydra uses, Hercules eventually kills the hydra. Okay, so the battle cannot go on forever. Therefore, if you fix in advance that the hydra will use sprouting numbers 1, 2, 3, 4, 5, then for each initial hydra, there exists an n such that no matter what Hercules does, the hydra dies in at most n steps. Okay, so this is a first order statement which cannot be proven in Peano Arithmetic, and the obvious proof is using this more general statement, but this is a second order statement, so you're kind of stuck. There are many other PA independent statements, Kanamori-Macaloon's regressive colorings, so the worms by Meklemishev, which were actually previously discovered by Hamano and Okada. There's finite miniaturizations of Drovskal's tree theorem, the graph minor theorem, a few other things. Okay, and there's this general tool for proving that something cannot be proved in Peano arithmetic. This result by Buchholz and Weiner, which is based on Gensen's cut elimination, which we mentioned before. So suppose that you have a Turing machine that computes a function. So a Turing machine, given an input on the tape, the machine runs until it stops, and then what's written on tape is the output. And suppose that the Turing machine always terminates. And suppose that Peano arithmetic can prove that the machine always terminates. Then the function computed by the machine cannot grow too fast. That the function computed machine is bounded by some function in the fast-growing hierarchy below epsilon 0. Okay, so basically, almost all of the above independent results can be proved by using this, because in all those cases, there's some, if you calculate the function, it grows like f epsilon 0. And that means that Peano arithmetic cannot prove the relevant thing. Okay, so let's get back to fusible numbers. So here are some second order statements regarding fusible numbers. F is well ordered is a second order statement. Algorithm M terminates on non-real inputs is a second order statement because it quantifies over real inputs. But we have some first order statements about fusible numbers. For example, you can say for every A, every natural A or every rational A, there exists a smallest fusible number larger than A. Okay, so this is an immediate consequence of the fact that the fusible numbers are well ordered. And algorithm M terminates on natural or all rational inputs, as we said, is also a first order statement. Every subfusible number has a maximum height representation. Okay, so all these first order statements follow from the fact that F is well ordered, and all these first order statements are unprovable in Peano arithmetic. That's our main results regarding Peano arithmetic. The proof is like this. Okay, so this is a claim. These three statements are unprovable in Peano arithmetic. So the second statement regarding the algorithm M, we already proved because we already showed that it grows, its inverse grows like f epsilon 0. So immediately by Buchholz and Weiner, it follows that it's unprovable in PA, determination of algorithm M. Okay, and then since we know that PA cannot prove that algorithm M terminates, in order to prove that the first statement, this first statement for every A, there exists a smallest fusible number larger than A. So what PA has to do is to prove that if M does not terminate on some input X, then there exists an infinite descending sequence of fusible numbers converging to X. You have to relate the algorithm to the non-termination of the algorithm to an infinite decreasing sequence within Peano arithmetic, which means basically that you cannot use any infinite sequence in your arguments. Okay, this statement is a first order statement, even though it says infinite descending sequence, it's okay. Okay, and therefore.
So, excuse me. So you mean that there is a specific description of such a descending sequence,
right?
Which you refer to in this statement. Not, you don't quantify over infinite.
Yes. So
you may say computable descending sequence, something like that. Then you can quantify.
Right. You can prove that for every n, there's a fusible number between x and x plus 2 to the minus n. And that comes from the
okay.
You assume that M has an infinite recursion tree that goes down infinitely, and you get from that infinite tree this smaller and smaller fusible numbers that are above X. It's a little technical, but it's not the end of the world. Okay, and then regarding the maximum height representation, is like this. If we know that every fusible number has a maximum height representation. The reason is because if a fusible number has a representation of height n, then
excuse me, so you didn't actually define what is a
height, right?
Right.
Yeah, so sorry. So here's a definition by picture. So this this is the height of this representation is 3. This is 0, 1, 2, 3.
And this 3 is just the term using this fuse operation, right? Which generates your, okay, so you start from bottom and then come to the, okay, so 0 fuse 0 is 1/2 and so on, right?
Exactly.
Okay, so that's the depth of this term, okay.
Yeah, so it turns out that every fusible number, fusible numbers can be represented in many different ways with different heights, but there's always a maximum height. Every fusible number has a maximum height. Why? Because if, I didn't write this here, but if Z is a fusible number which has a representation of height n, then Z plus 2 to the minus n plus 1 is also fusible. So if Z had representations of arbitrarily large heights, you will get an infinite descending sequence that converges to Z, which already proved that is not the case. So we know, Peano Arithmetic doesn't know, but we know that no fusible number no fusible number has representations of larger and larger heights. Okay, and in order to prove that Peano Arithmetic cannot prove that, you prove that if Z has a maximum height representation n, then not only this guy is fusible, but it's the next fusible number. And therefore, if Peano Arithmetic could prove that every fusible number has a maximum height representation, PA will conclude that for every A, there exists a smallest fusible number larger than A, which is this guy, 2 to the minus height plus 1. Okay, and since we know that this cannot be proved, then this can also cannot be proved. Okay, that's how the three statements are linked to each other. Okay, so that's basically our main results, and it's just a few other things. So suppose you are given a number x, and you want to know whether it's fusible or not. How will you do that? So one way will be to try building all possible fusible numbers until you find it. But then if x is fusible, you will terminate in some finite amount of time. The question is, what happens if a given number is not fusible? Maybe you'll keep going forever and ever trying to build it. But actually, we have an algorithm that can decide whether a given number is fusible or not. It's in this, it has some kind of loops and stuff. So this algorithm is like the M algorithm, sort of finds the next fusible number, but not the next 10th fusible number, but the next fusible number in general. It has a loop here. And this algorithm number 3 finds the next fusible number, including the number itself if it's fusible. So if the given number is fusible, it returns the number itself. So to decide if a fusible number is, a given number is fusible, you call algorithm 3 and see whether it returns the number itself or not. That's our algorithm, okay? Won't get into the details. There's this conjecture which we mentioned, and it's like this. We conjecture that this method gives you all the fusible numbers. You don't miss any fusible number. It's it's very similar to the construction of the tame fusible numbers, just a little different. Okay, so if you construct, suppose you already constructed all the fusible numbers up to x plus 1. So you go one distance one left up to x, and you get the next fusible number and the next and the next omega fusible numbers, and we know that their distance decreases by a factor of 2 in each step, and then you divide the interval between x plus 1 and going m to the right, you divide it in this way. And you want to construct, let's say, the third interval, then you take this interval, which is twice as large, and you fuse them all with this, with the third guy over here. Okay, it's very similar to the 10 fusible numbers, and we ran some computer experiments, and we didn't find any counterexample to this. Okay, and if this is true, then you get many things. You get an upper bound in which the tower of omegas doesn't increase by 2 in each step, but only by 1. And you can, I guess, you can also get an upper bound for the density, because these guys also have some ugly looking recurrence relations, like I showed you for the 10 fusible numbers, just a little different. If you could prove this, you could prove a few things. Okay, so open problems, as we said, the upper bound for the distance, the inverse distance to the next fusible number. There's some of these algorithms, let's say this algorithm for sure takes a long time to run, but this algorithm, we don't know exactly if it runs quickly or slowly. So we figure out the running time of these algorithms, the conjecture we just mentioned, and also we noticed that if a fusible number has representations of heights h1 and h2, then it always seems to have representations of all intermediate heights. Okay, and that we found, but we don't know how to prove that. Okay, and thank you very much.
Okay, very nice. Immediate question. So if you, so the actual upper bounds for running time that you have are of order f epsilon naught. Is that so? For this algorithm, for example, for testing whether the number is fusible or not, given the rational number determined whether it's fusible.
Right. So, I guess. Yeah.
And so this open question means that you don't really have any lower bounds for this.
It might be that this algorithm actually runs very quickly. This algorithm, because when you run this algorithm, the successor algorithm on the natural numbers 1, 2, and 3, and so on, it takes a long time. Because, for example, for 3, its answer is this 1.5 billion thing I showed you at the beginning. But this algorithm, if you feed them with the inputs 1, 2, 3, then it runs very quickly, because subtracts 1, then subtracts 1, then subtract 1, and that's it. And when you get to 0, you are done. Then you're done, you're done, you're done, and that's it. Okay, so if the first, in that case, it runs quickly, and I guess it might be that it always runs quickly. It might run in a long time if you give it a complicated input, but if the running time is as a function of the size of the input, then that's okay. So we're not sure.
So you conjecture that, so it's plausible that this algorithm 3 is actually something like polytime algorithm, for example.
It might be polytime, yeah.
Only you don't have a proof that it's polytime. That's
right.
The status of this question. Okay, very good, very good. Okay. Okay, so let me now ask the audience for any other questions to the speaker. Yes. Okay. Well, while the people are thinking about their questions, so let me.
Something in chat. Okay.
There is a.
That's private to me.
So. Okay. But anyway, I think this principle that you discovered is very nice, and actually what makes it, I think, interesting is that, so you're basically dealing with this very simple to define embedding of epsilon naught into the rationals, and somehow having this embedding, so not only epsilon naught itself, but so to say the whole structure, the whole embedding function allows you to define very naturally these things like density and these parameters, which then give you these unprovable statements. So that's, I think, a very nice feature of this construction.
Thank you.
Okay. So what do we have here in our chat? So Fedya, any other questions? Maybe.
No, not really. No, okay, it's yes, it's because it's very interesting result, but yeah, I think it was very clear talk.
So definitely there are some questions one might want to think about. Further questions here. So thank you very much. So that was very interesting and nice.
Yeah. So I think, Gabriel, I think you actually haven't answered the question that I asked you before. So about this tower of omega exponentiation. So you have this like four omega exponentiation. So basically, when you give this estimate for d function, right? So you use this you basically use this tower for omega exponentiation to get to Hardy function.
Okay.
Yeah, and so so what I asked was do you have an idea how optimal this is? So do you really need for tower four omega exponentials, or you could get away, say, with tower of 2 or something like this?
So in the upper bound, we get a tower which is twice as high as the lower bound, right?
Okay. I think I missed this. Yeah.
The upper bound, okay. Okay, here. The tower in the upper bound is twice as high as the lower bound.
No, I'm talking about the difference. So the even earlier slides where you gave this so
here.
No, even before. So when you talk about d function and Hardy function,
this.
No, it was before. Yeah, about it was about the same fusible numbers. So even earlier. Yeah. Okay. We are earlier. Okay.
Let's do like this.
No. Okay. Oh, wait a second. So what was it? Yeah. So yeah. Okay. So this lemma.
This one. Yes.
And so here you have this tower for omegas, right?
Right. Yeah. Here.
Yeah. And yes. I wondered how optimal this is. So.
I see. It might be that you need only 3 omegas, but 2 omegas, you run into difficulties. It's like these recurrences are very quirky. They don't behave the way you want them. So, but if you put them in top of an omega, then it becomes a little nicer. So I needed 4 omegas to get this thing to work, and it might be that 3 omegas are enough, but 2 omegas we run into trouble. It's just to make the thing easier.
Yeah, I see.
It might also grow fast even with the 2 or 3 omegas. I don't know. Yeah.
Okay.
Okay, so if there are no more questions, then we are about to to close our seminar.
Thank you very much.
Thank you very much. That was very interesting and I think very
Nice to meet
refreshing
you.
talk. Yeah. Thank you. Bye bye.